All right, now it's time to work on one of the trickiest concepts of this unit, and that is sketching the derivative function graphically. So what we want to be able to do is take this function, which is f, and then on the axes below, we want to go ahead and sketch f prime. So what I like to do when I teach this is to have you guys write down steps and then follow the steps and do this in a very structured way, because if you try to do it holistically, you will get very confused, and I don't want that. So the very first thing we're going to do is come up with the rule, the first rule to follow, and that is going to be to find where there are horizontal tangent lines on the function f. So you want to find where f has horizontal tangents. And where f has horizontal tangent lines, that means that f prime is going to equal 0. So let's come over here and we see that we have a horizontal tangent line here, here, and here. So I can go down to the sketch of my derivative and start it by plugging in x equals 0 at -2, maybe -0.2, and around 2.5 or 2.6. So again, this is all estimating. We're not going to find exact values yet. So then the next thing I do is that I want to understand where there are points of inflection on f. So where f has points of inflection, that means that f prime has turning points. So I'm going to write that out, turning points. And while I can't sketch those in quite yet down on f prime, I can label the spots where there are points of inflection, and that's going to enable me to continue my sketch. So it looks like I'm concave up and then concave down and maybe have a point of inflection there. Then I'm concave down to concave up, and perhaps there's a point of inflection there. So what this has enabled me to do is it's given me 1, 2, 3, 4, 5, 6 separate sections of my function to look at. And what we're going to do is look at each piece separately or individually and very methodically. Like I said, do not try to sketch the derivative graph holistically. Let's go piece by piece. So my first piece, my function is decreasing, which means that my derivative will be below the x-axis, and my function is concave up, which means my slope goes from very, very negative towards 0, so my slope is increasing. So on my derivative function, I need a negative but increasing derivative. So I just need to sketch in that section as negative and increasing. So let's talk about this. We have f is decreasing. That means that f prime is below the x-axis. When f is concave up, we know that f prime is excuse me, I didn't mean to do a greater than. I meant to say increasing like that. So then my next section right here, this is the second part of my graph. My function is increasing, so that means my derivative will be above the x-axis. My function is still concave up, so its slope is still increasing. Do you see how it starts at 0 and it goes positive? So I can put those rules here. If f is increasing, the slope of f, or the derivative, is greater than 0. And if f is concave up, excuse me, I'm still on concave up, f prime is still increasing. So I need a little section between -2 and about -1.25 where my derivative is positive and increasing. My next section of the graph, my function is still increasing, so my derivative is still positive, but now my function has turned to concave down. So I take a positive slope and then I tend towards 0 slope, which means that my derivative is decreasing. So that means on a concave down portion of f, my derivative function is going to be decreasing. So I need to connect here. I have now a decreasing and positive portion of my derivative graph. My next section of the original function looks to be a decreasing function, so a negative slope, negative derivative, concave down function, so a decreasing derivative. So let's connect here. I now need to have a negative decreasing derivative function all the way to about 1.2. My next section here, my slope is still negative, so the derivative will still be negative, but now the function is concave up, so the derivative starts increasing. So I basically can connect up to the next x-intercept. So I have a negative derivative, but an increasing derivative. And then the last section of the graph, the slope of this graph is positive because the function is increasing, and the slope is increasing because the function is concave up. So I can finish off my derivative graph by having an increasing and positive section. Last thing I want to point out, well, let me point out these two items from numbers 1 and number 2 here. Remember where f has horizontal tangent lines, that means its derivative equals 0. So where I drew in the horizontal tangent lines, see how I have x-intercepts at those points. Where f has points of inflection, have you noticed that that is where the derivative of f has turning points? That is something key to remember. F has points of inflection, f prime has turning points.